Hi, Math 8 students. So this week we'll be wrapping up topic 7. Probably Friday we'll do a little intro to topic 6 in our kind of further into distance learning. So today we're going to do Pythagorean theorem, but we're going to do a special applications. We're going to try to use it to find distances in coordinate planes. And these are incredibly useful tools. So that'll be kind of our goal for today. So first I'm going to reference the exploration problem I posted last Friday. So if you didn't do that problem, go ahead and pause the video. You can either get it from the PDF on the Schoology page, or you can just pause the video and literally do it from this example right here. And so we got Jim, and he's claiming that this marked yellow path, and we can look at the marked yellow path here. I'll go ahead and draw over it so we can see. And he's claiming that if you're trying to get from this castle here, marked at this star, to this clown tent here, kind of a very strange tent. I would never go in that tent. And he claims that this path along the yellow line is the shortest path. And so just for reference, let's find that distance really quick. So we've got kind of some little conversion factors. So we got a grid square is 1 centimeter by 1 centimeter. So this distance across is 1 centimeter. So we can just count the grid points. 1, 2, 3. That's 3 centimeters. Over here, that's 2 centimeters. If we can do 3 plus 2, that's 5 centimeters in total. And then we could just do a quick conversion factor. So let's do, it's 5 centimeters per, well, we don't really know the feet yet. So let's just label that as question mark in, just do FT for feet. And we can just set up an equivalent ratio really quick. So we know that 1 centimeter is 500 feet from this conversion factor right here. And then we can just go, okay, well, let's just solve for that really quick. So move this over, give us some room. We know that I just need to take everything, multiply it by 500. So multiply 500 here. That means we need to multiply our 5 centimeters by 500. And if we do that calculation, we get 5 times 500, which gives us that unknown variable of 2,500 feet. So if I walk from here to here, and I follow along the yellow path, we know it's 2,500 feet. So let's just keep that for reference. So now let's look at his claim. So, his claim is that it's the shortest path. And so if you kind of know, you might have heard this phrase before, but we also know that the shortest distance between any 2 points is a straight line. So the question then becomes, well, if we were to draw a straight line between those 2 points, we would get something that looks like that, just straight across, not going around, just cutting straight through the grass here, and partially through this, I guess, ice cream truck. It almost looks like a little ice cream at the top. Not really sure. But we need to find what this distance is. So let's use our coordinate plane to lend a hand on this. So if we were to put this on a coordinate plane, we basically have 2 points here that we're looking at. So we can count over, we got 1, 2, 3, 4 is the x-coordinate. So this is at 4, and then up 1. So 4 comma 1 is that coordinate. And we could also count over here. So we got 1 over 1 to get to here, and then up 1, 2, 3. So 1 comma 3 is that coordinate. And you'll notice I just placed it over here. So we got 4 comma 1, and we've got 1 comma 3. And one thing you might have noticed from coordinate planes, at least Cartesian, the ones we've been dealing with, is each one of these boxes has essentially a whole handful of right angles. So right angles, right angles, right angles, and that lends to basically taking this and creating a right triangle. And there's just a ton of right triangles. Any 2 points, we'd have a right triangle, we could draw through them. And so we essentially have an ABC right triangle, and we can see what this distance is. Pardon my pun for C, but we could find what this distance is. So all we have to do is label what we know, and then we've basically got a pathway to a solution. So what I could do here is I could say that if I wanted to investigate this, we already know that this is 1, 2, 3 centimeters. So we'll go ahead and label that. We know that going up, we just go 1, 2. 2 centimeters. And we could just solve for c and find the straight line distance between these 2 points here. So what I'm going to do here is I'm just going to set it up as a Pythagorean theorem problem. So I could say that 2 squared plus 3 squared equals c squared. So I'm just using a squared plus b squared equals c squared. We could solve for c. So I go through and I solve it. So let's just evaluate. 2 squared is 4. 3 squared is 9. And now we just simplify. So 4 plus 9, we get 13 equals c squared. And then we can just go ahead and solve that. So square root both sides, and I should get a solution of c, and I'm just going to approximate it because square root of 13 gives a very long repeating decimal. In fact, it's irrational. Gives approximately 3.6, and let's put our units back on there, centimeters. And we can just do a quick conversion back. So we got 3.6 centimeters per, we don't know how many feet, and we could just set that equal to our sort of conversion factor. There's 1 centimeter per 500 feet, and we know from that that 500 is just our multiplier. So multiply by 500, we know we just got to multiply 3.6 by 500 to get the amount of feet. So times 500, and we will get approximately 1,800 feet. Which, if we go back to our previous one, we knew that this distance across going up here and over here was 2,500 feet. We know that approximately 1,800 feet quite a bit quicker. And we can just find that straight line distance pretty easily just by applying that Pythagorean theorem. So let's do an example on this real quick. So let's just say I didn't have any context, and we're going to take, we'll call this point A, and actually let's call this, because I don't want to confuse it with a squared and b squared. Actually, we can just give it uppercase. So instead of lowercase like our Pythagorean theorem, let's give them uppercase. So we'll call this point A, point B, and we want to find the distance. So first, let's go ahead and just write their coordinates really quick. So here, it's an x coordinate of -3, so we'll put that first, and then it's up 1. We got our points. And then we've got a coordinate here of 5 for our x and 5 for our y. And we're just going to go ahead and set this up as a Pythagorean theorem problem. So all we're going to do here is we're just going to go through and we're just going to set it up as a right triangle. So as you can see, I can just set this up as 2 distances here with a right angle. So I'll go ahead and plug in. So first, if I were to go up here, I could say that this is like a distance of, or -3 to 5. I could just count across, go 1, 2, 3, 4, 5, 6, 7, 8. Or I could do like y2 minus y1 like we did in unit 2. So 5 minus a -3 is a distance of 8 to give us this distance. So either way, you can just count across. And then we know we got to go up 1, 2, 3, 4. Same thing as 5 minus 1. And we get 4. So we've basically got a right triangle where we know A, we know B, and we just need to find C. So we're going to set it up as a right triangle problem. So a squared plus b squared equals c squared. We know A, it's 4. We could always interchange them, but just pop 1 in. We know B, it's 8. And that's going to be equal to c squared. So we've basically set up a right triangle. Now we're just setting up this Pythagorean theorem equation, and we're going to solve it. So we just need to evaluate, balance it up, and we're good to go. So to start, we'll just evaluate what we know. So 4 squared, that'll give us 16. 8 squared, that'll give us 64. That'll equal c squared. And then we'll just add them together. So 16 plus 64, that gives us 80. And now we just take the square root. So we'll go in, square root both sides, square root both sides. And this one is certainly not one that I memorized, so I'm just going to calculate it really quick. Square root of 80 is 4 times the square root of 5. But let's get an approximate answer, about 8.9. So do that, I essentially have, we can just fill this in. I know it's approximately equal to 8.9. And quite easy to just apply this to any old coordinates. As long as we have 2 points on it, we just find the distance by taking the change in x, how far the x distance, how far the y distance is, and just turning that into a right triangle. So just to kind of circle back to the beginning, because this will kind of be our wrap up of topic 7. So we basically have this Pythagorean theorem that we can find distance between 2 points on a coordinate plane. And a lot of people kind of take it to, well, it's just for XY graphs, and they kind of leave it there. But there's so many other applications of this that I thought it might give you a preview of where you might see this as well. So a lot of times, if this is just for 2 dimensions, so you got an up, you got a left, or you got an up down, you got a left right, but we could also tack on, and this is very common in kind of higher level math, tack on kind of a third dimension. Picture this Z kind of coming in and out of the screen, trying to notate that as best as possible. And so big time that this will use is they also have a way to kind of apply this in 3 dimensions as well. There's kind of like a 3-dimensional Pythagorean theorem distance formula. So we won't get into how that's calculated. You can look it up if you'd like, but kind of just an application is anytime you see like a waypoint system in a game where you like set a waypoint and it tells you how far it is, and it'll kind of put up a little kind of dot on the screen to see where you're going. So just to kind of give you a visual on this, I just brought a kind of a screenshot promotional picture for Breath of the Wild. So let's say you are Link. So for Link, for the game kind of programming, they'd set Link to the origin. So like Link is his own origin system. So he's going to have an X, Y, and also remember it's 3-dimensional. So think of this as like jutting off in and out of the board or in and out of your screen, Z. And so they would probably set length to 0, 0, and he's got a third coordinate because he's at 0 for the y, 0 for the x, and 0 for that third component. And if they were ever to try to like set a waypoint, let's say I want to navigate to this tower. So you set a waypoint. So what the game's going to do is it's going to say, well, what is the coordinate in our game world of this tower? So it's going to have an x coordinate, it's going to have a y coordinate, it's going to have a third coordinate. And what it'll do is it'll actually say, well, what's this distance that's over in the x? So how far over in the x is it? And we'll kind of draw that over. Again, we're kind of messing with perspective here, so keep in mind it'll be a little bit off. And then we say, well, how far is it in the z? And we kind of go over this way. And then we also say how far over it is in the y, and it's kind of hard to draw at this point because I'm drawing on a 2-dimensional plane, but you kind of get the picture. You can triangulate this distance on a coordinate system, and it'll calculate it, spit it out as a function, and it'll tell you the distance to your target. So kind of a weird application. So again, if you have any questions on this, please bring them to the office hours on Wednesday. We'll probably do like a little review game for this. So I will see you guys later.